Good day, folks. Let's look at the topic called power in work energy and power. Let's define power. What is power? According to an exam guideline, the power you have to define it this way: it's a rate in which the work is done. That's all you define it. It's the rate in which the work is done. Now, in a nutshell, or in our everyday example, how do we call power? It's how quickly the work is done. It's how quickly you do the work. Now, for example, you are taking a box from here to here. Let's say if it takes 2 seconds normally to take that box, if you take 1 second now to take that box, that means the power that you have used there is greater. Now, if you look at the formula for power, power is equal to work done over change in time. Now, there's a proportionality between the power and the work and the power and time. The shorter the time you do the work, the greater the power, right? The shorter the time you do the work, the shorter time, greater power. Longer time, smaller power. While the work has been done, you are doing the same work. So when you're looking at the relationship between these two, this one must remain constant. Now it says for the same quantity of work, the power for the shortest time is greatest. So for the same amount of work there, the power is greatest in the shortest time. They are inversely proportional there. Here's another formula for power. Average power is equal to force times velocity. Now it says when a force moves an object with a constant velocity, the power average is that one. So if an object is moved by a force at a constant velocity, so you use this formula. So this velocity must be a constant, and this force is the force that moves an object. So it can be force of a motor, or it can be a force of an engine, or a force applied, any force that moves an object. That now the units for power, guys, it's watt. It's very important. It is not necessary to distinguish between minimum and maximum power, whatever. Now calculate power, two strategies for information. Okay, guys, let's leave that. Now, for a constant velocity, it's very important to remind ourselves that the F net is equal to 0 there. Now, this is the formula for power, and this is another formula for power. Now, first calculate the work done by. Now, to calculate power, guys, you need to calculate the work done, which is the formula for work done is that it's force delta x cos theta, and then once you get the work, you substitute there, and then you divide by the given time there. Now let's say the power now you need to calculate is the power delivered by an engines or strings or pump that work non-consecutively conservatively. Therefore, the work done by an appliances can be calculated. But now when you calculate the power that is delivered by engine, string, and pump, which is non-conservative forces, so you need to calculate the work done by non-conservative, which is, let's say it's a force of an engine. Force of an engine, it's a work done by non-conservative. You calculate that work done, and then you calculate time, which is how do you calculate the work done by non-conservative? You use the work energy theorem there. Here's an example for power. It says the engine of a 290 kg motorcycle exerts an average forward force, which is the force of an engine of a motorbike or motorcycle, is 4,000 newtons. So this one is the force of an engine over a distance of what? 25. This is a displacement that it has traveled. The motorcycle takes 0.8 seconds to travel the 25, so that's the time. Now, guys, we're given the force of an engine of the motorbike and the displacement and the time it took. Now, the question 1, it says calculate the work done by the force of an engine. So, number 1, work done by the force of an engine, delta x cos theta, right? Very important. The force of an engine is going in the same direction with the displacement. The angle between them is 0. So we substitute the force of an engine and the displacement is 25 cos what? 0, which is 1. So it's going to be 100,000. It's going to be 100,000 joules. That's the work done by the force of an engine. Let's go to number 2. Number 2, it says calculate the power generated by an engine. So we wanted the power, how quickly the energy was transferred by the engine. So power is equal to W over change in T, which is our W. It's a work done by the force of an engine, right? So it's 100,000 divided by the time it's 0.8 seconds. 100,000 divided by 0.8 seconds, it's going to be 12,500 watt. So now we can change that if we want to, but we're not told. We can change that into kilowatts. We divide by 1000, so it's going to be 12.5 kilowatt. Those are the units for power, which is, it's what you can leave it here or you can leave it there. Let's look at an example 2. Example 2, it says Mercedes C63 AMG with the mass of 1700 reach a speed of 0 to 25. This is an initial velocity and the final velocity and the time, right, of that AMG. Now it says calculate the car's supplies kinetic energy won in this time. So when the car travels from 0 to 25 in 3 seconds, it has gained in energy, which is the kinetic energy. Now the question wants us to calculate that kinetic energy there, right, which is the change in kinetic energy from 0 to 25, right? So the change in kinetic energy we calculated by half mv final square minus mv initial square, or we can use that formula. It says change in kinetic energy is equal to half mv final square minus half mv initial square. So it's the same thing, it will yield the same answer. It's half times 1700, the final velocity is 25 square, minus 0 square, which is the initial velocity. So when you punch that in the calculator, it will give you 513,250 joules. That's the energy that it has gained, which is that's the surplus kinetic energy won by the car at this time, right? Number two, calculate an average power output for car's engine. So now to calculate the average power is equal to W over change in T. So where is the work done of the car by the engine? Now since the work net is equal to change in kinetic energy, now we have the work done. So we have the kinetic energy, so which is equal to the work done. So we'll take this work done and substitute it there. So we'll say power is equal to work net over change in T, or we can say the power is equal to change in kinetic energy over change in T, and then we have the change in kinetic energy there. That means that's the work that has been done. 513 250, we divide by the time, it's 3 seconds. We divide by 3 seconds. When you punch that in the calculator, the answer there, it will be 177,083,33 watts. So when we change that into watts, we divide by 1000, so it's going to be 177,08 kilowatts. That's how you change that. That's how you calculate the average power. Now it says in number 3, how will the power output of the car's engine changes if it reaches the top velocity in a short time interval? Now this is asking, this has reached 25 meters per second in 3 seconds. What will happen to the power that the car will deliver if it does that in a shorter period of time, let's say 2 seconds. Now, it's very important to understand that for the same amount of work, delivered by an engine, or we can say the engine will do the same amount of work. So the car will do the amount of work. So the only things that you're comparing there, you're comparing the power and the time. We're told for a short period of time. For a shorter period of time, what will happen to the power? The power will be greatest, but for work will remain the same. So now already the engine will do the same work. Already mentioned that. So now, but in a short period of time, right? The work that has been done now, it will be done at a short period of time. Now, very important, power will increase. Power will increase if the time decreases. Very important. If the time decreases, the power will what? Will increase, right? Will decrease when? During the work done. During the work done, right? And another thing that is important, its power is inversely proportional to time. You can put it like that. Hope you get that, guys.